So section 5, limits at infinity. We're learning how to talk about a function's end behavior in this section. We talked about end behavior before, back in Algebra 2, and probably in pre-calculus as well. But not to the extent that we're going to talk about it here. So take a look at the graph at the bottom of the screen. In this graph, the function appears to approach an imaginary boundary as x gets infinitely large and infinitely negative. Okay, infinitely more positive and infinitely more negative. So by that I mean as x goes to plus or minus infinity. Okay? This boundary is a horizontal asymptote. And so we have vertical asymptotes, but we also have horizontal asymptotes. The function approaches the asymptote but does not cross. That's not always the case with horizontal asymptotes, but for now, that's what we're going to talk about. So if you look, what does it seem like the horizontal asymptote might be at? 3, yeah. So if I kind of draw a dotted line, it seems to be kind of sitting at 3, and it is. So what we do is we analyze the graph and we say, as x goes forever in this direction, as the x coordinates become infinitely more negative, the graph seems to kind of get stuck at 3. And as x goes infinitely more positive, so as x grows and grows to the right, the graph seems to get stuck at 3 for the y coordinates, because it does. Okay, so the limit as x approaches infinity is 3, and the limit as x approaches negative infinity is 3. And what that is doing is it's saying there is a horizontal asymptote at 3. The graph is getting stuck at 3. Okay? So that's what we're studying in this section, basically, is horizontal asymptotes. So you have a theorem here that's going to help us get through the section, and it's actually really important. Your limits at infinity, if r is a positive rational number, and c is any real number, then the limit as x approaches plus or minus infinity of this rational expression, c over x to some power, r, that limit is going to be equal to 0. And what that means is you have a horizontal asymptote at 0. Okay, basically it's the x-axis, or the equation y equals 0. So if you have like 1 over x squared, you're going to have a horizontal asymptote, and the horizontal asymptote will be the x-axis. Or if you had like 7 over x to the 5th power, you're going to have a horizontal asymptote at the same location. Or 22 over x to the 63rd power, okay? You're going to have a horizontal asymptote on the x-axis. The usual rules for limits still apply, such as treating each individual term separately. All of the rules for limits that you learned before still are active here. Remember, if there's a limit as x approaches plus or minus infinity, then this means that the function itself is approaching a horizontal asymptote as x increases or decreases without bound, okay? So when you see a problem that's asking you to find the limit as x approaches plus or minus infinity, what it's really doing is asking you, is there a horizontal asymptote here? So you have to remember that, and you have to understand that it's really asking you, it's kind of like the directions are saying, find the horizontal asymptote if there is one. Okay? So find the limit in the example. The limit as x approaches infinity of 5 minus 2 over x squared. So to do this one, you're going to have to remember that the usual rules for limits apply. and that is that you can take the limit of each term individually. So what we're going to do is say, okay, I can take the limit as x approaches infinity of 5, and I can take the limit as x approaches infinity of negative 2 over x squared. So what's the limit as x approaches infinity of 5? Yeah, it's 5. Okay. Think of like if I direct substituted infinity into x, there's no x to direct substitute infinity into, so I'm just going to get 5. All right? Then minus, now what is the limit as x approaches infinity of 2 over x squared? It's 0. 1, I could think of direct substituting infinity in and just have 2 over infinity squared, which is still infinity. 2 over infinity is like a really, really, really tiny number, right? It's basically what? It's basically 0. Good. Or I could think of this rule that I just gave you right here that says the limit as x approaches infinity of a constant over x to some power is equal to 0. Okay? So 5 minus 0. So what's the limit? It's 5. So now that we've done that example, and I gave you a different way to think about this problem, if you come back up here and think, okay, I can direct substitute infinity in. If you direct substitute infinity into the denominator up here, I have a constant divided by infinity to some power. It's going to be, it doesn't matter what this number is in the numerator, divided by infinity, what am I going to get? I'm basically going to get 0, okay? And that's why this result is 0. And that's what's going to give me this horizontal asymptote, okay? The denominator takes over, and I wind up with basically 0 in the limit as x approaches infinity. All right. So let's do these examples here real quick. Find the limit as x approaches infinity of f of x. So let's write this as notation first. This would be the limit as x approaches infinity. And really I can write f of x here just because I was given the name of this function. I can write it that way. And what would the answer be?
0.
Yeah, it would be 0. And then how about the limit as x approaches infinity, again, of f of x?
0.
Also 0. And now this one. So if I were to direct substitute infinity into that first one, I'd have 3 over infinity squared, which is basically 0, so that's why I get 0. If I do that again for the second one, I'd have 1 over infinity, which I have basically 0 again, okay? But if I direct substitute infinity into the third one, I'd have 2 times infinity minus 1. So 2 times infinity is infinity. Infinity minus 1 is infinity. And then infinity plus 1 on the bottom would just be basically infinity. So I have infinity over infinity. Infinity divided by infinity is not 1. It's not 0. It's not infinity either, okay? It's the indeterminate form. Kind of just like we had 0 over 0 before when we were dealing with limits, okay? This is another style of the indeterminate form. So what we need to do is we need to manipulate this thing a little bit before we're able to actually evaluate the limit. And the hint that I give you is right here. Divide the top and the bottom by x. We need to manipulate it a little bit. So we divide the top and the bottom by x. So I'm just going to kind of squeeze this in here. Divide the top and the bottom by x. I'm not changing anything. I'm just kind of multiplying in a 1 over x to the top and the bottom. So it's kind of like multiplying in a fancy 1. Okay? So when I do that, now I have f of x equals, what's the new numerator?
2 minus 1 is 3.
No, 2x over x reduces to what? 2. And then minus 1 over x. Over x is 1. And then plus 1 over x. So now I can take the limit as x approaches infinity of f of x. And basically I can direct substitute the infinity in now. And when I do that, I have the 2, of course, plus 1 over infinity, which is what? Minus. Minus essentially 0 over 1 plus, again, essentially 0. And so I'm just left with 2 over 1, which is 2. So a little bit of manipulation there allowed me to come up with the answer. Okay? I have more examples that deal with this type of math. Let's try this one. Again, if I direct substitute infinity, so I take the limit as x approaches infinity of the function, you get infinity over infinity again. And I don't like that, right? I can't, that's an indeterminate form, so I can't do anything with it. So what I need to do is manipulate this thing, okay? I need to somehow free up a term. So what could I do similar to what I did last time? By x, we'll free up one term in the numerator, but not a term in the denominator. So yeah, look at the denominator. I see the x squared. I like to divide by x squared here. Top and bottom, though, it has to be like a fancy 1. So when I do that, f of x is now the limit as x approaches infinity of, and I don't have to write f of x every time. Remember, you can write the function itself. So this is now what? 2 over x plus 5 over x squared over 3 plus 1 over x squared. So it's really important to free up a term in the denominator, okay? Just dividing by x in the numerator was okay, but it didn't free up a term in the denominator. We really need to free up that term in the denominator. So now if I direct substitute, I have infinity in that first term in the numerator and the second term in the numerator. So what happens in the numerator?
0.
Yeah, I get 0 just in the numerator. And in the denominator, what happens? I get 3. So I have 0 over 3. So the result is what? 0 is the answer. Everything's going to be fine. How about the second one? What should I do? X squared again. Top and bottom. So now this time I have the limit as x approaches infinity. And again, I'm just going to write down what the function's result is. So what do we get?
2 plus 5 over x squared. All over 3 plus 1 over x squared.
Okay. There's squared there. All right. So now if I direct substitute the infinity, yeah, 2/3. Good. And how about the third one? Another x squared. I'm not taking out x squared, I'm dividing.
X cubed.
Nope. It's the denominator that's important because of the division by 0 that's going to happen, or the division by infinity that's going to happen. I have to free up a term in the denominator, okay? So I'm going to have the limit as x approaches infinity of what? 2x plus 5 over x squared over 3 plus 1 over x squared again. And what do we get in the numerator when I direct substitute?
2x.
I get 2 times infinity plus 0. So that's going to be 2 times infinity, which is infinity over what? 3. And what is infinity divided by 3 going to give me? just infinity. So the result on this one is infinity. Okay, now what is it we're finding here? What did I find when I got an answer of 0 on this first guy? The horizontal asymptote. So the horizontal asymptote was at 0. Okay, so this is like the equation y equals 0. And what did I find here with this 2/3? Exactly. So I'm actually going to write that down. The horizontal asymptote here was at y equals 0. And the same thing here. Horizontal asymptote was at y equals 2/3. That's the horizontal line that goes through 2/3. What did I just find here? No horizontal asymptote. Okay. Actually, there is something going on here. The examples that I just gave you are not chosen by accident. The numbers are all the same. Yes, the exponents are the only thing changing. And I did that on purpose because I wanted to see if you guys could figure out what was happening. Because you've learned this before. You've learned horizontal asymptotes before in pre-calculus, or at least you should have. I want to see if you can remember what it was or what's going on here. See if you can figure it out. Go ahead. So here's a summary of what we just saw. Common limits at infinity. So if R is positive and rational and C is real, this first one is the theorem that you just saw. So the limit as x approaches plus or minus infinity. C over x to the R power, the limit is 0. If the degree of the numerator is less than the degree of the denominator. So this is the first example that you were just looking at. The limit's going to be 0. Okay? And this should be of. If the degree of the numerator, here's what I get for copying and pasting. If the degree of the numerator is equal to the degree of the denominator, the limit is the ratio of the leading coefficients. And that was the second example. The leading coefficients are the numbers in front of the term that has the highest degree. It doesn't have to be the first term, it's just the term with the highest degree. If the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. Function isn't approaching anything. It just takes off and does whatever it wants. And I have one more to add here. If the degree of the numerator is exactly 1 more. Let me say 1 higher. It's a little bit better to say. 1 higher than the degree of the denominator. So if the degree of the numerator is exactly 1 higher than the degree of the denominator, that is what's called a slant asymptote. And we'll get into slant asymptotes at the end of this section. I think we'll see one, and then a little bit more in the next section. So you can think of these rules as implying that in a rational function, the higher degree term is the one that takes over, okay? As x becomes larger, the magnitude of x becomes larger, the highest degree term is the one that wins. If a rational function has a horizontal asymptote, the function will approach the same asymptote to the right and to the left, with one exception. If you're dealing with a radical involved, it's possible that there are two horizontal asymptotes, and we're going to see an example that has two horizontal asymptotes. They're kind of weird, and they're difficult to explain, but there are cases where there's two horizontal asymptotes. Okay? But for the most part, there's just one, and the function will approach as x becomes large. When x is small, the horizontal asymptote has no effect on the function at all. The function can cross horizontal asymptotes. Okay? Let me give you an example. So let's say, oops, I want to draw asymptotes as dotted lines. That's dotted. Stupid board. So I can draw a function, okay? As my function is getting large x values, it's going to be kind of stuck on that asymptote, right? As my function gets large x values, it's stuck on that asymptote. But it doesn't have to follow that asymptote when x values are small. Because those big terms, those big exponent terms, when x is small, aren't going to be as influential as the small exponent terms are, okay? So the horizontal asymptote does not have as much of an impact as the rest of the terms do. So the function itself can do things like this, okay? It can cross horizontal asymptotes. It can cross horizontal asymptotes several times. This is an allowable situation. Now, vertical asymptotes, the function can never cross, okay? But horizontal asymptotes, the function can cross when x values are small. When x values are large, the horizontal asymptote, the function is not going to be able to cross because the horizontal asymptote will take over and the function will wind up stuck, okay? So that's something worth remembering. All right. So functions that are not rational can have more than one horizontal asymptote. The functions that have more than one horizontal asymptote are usually going to have a radical involved, like I just said. These often occur where there is a root in the denominator. So, for example, find the limit to the right and left. So when you have a root in the denominator, you're going to want to find one-sided limits. So the limit as x approaches infinity from the right, so just do the limit as x approaches positive infinity, and then the limit as x approaches negative infinity, okay? Would be the best way to approach that. So just start off, first of all, by rewriting this guy, because if I plug infinity in right now, I'm just going to wind up with a disaster. So the first thing I'm going to do is get this thing rewritten. And I want to do like I did before, where I divided the top and the bottom by x. Okay? But the problem is, I don't want to, if I divide the top by x, I want to divide the bottom by x also. But dividing the bottom by x is going to be kind of ugly because of that square root situation. So how am I going to divide the bottom by x when there's a square root involved? What does it have to be? I can't divide by the square root of x if I'm dividing by x. I got to dress the x up a little bit. No. X to the 1/2 is the square root of x. And that's not x. I need it to be x because I want to divide the top by x and the bottom by x. But I can't divide the bottom by x. I need to dress it up a little bit. It needs to be x, but I got to like fake it a little bit so that it's not just x. That's just 1. It's dressed up, but it's not quite right.
1 over x to the negative 1.
No. It's already in the bottom. I don't have to put a negative exponent on it to make it think that it's in the bottom. It's already there. How can I dress x up? I need to fit it into that radical because I can't just divide by x. That's not going to do me any good. I got to dress it up so that it can sneak its way into that radical. Yeah, square root of x squared. That's just x, right? And that'll allow me to sneak it into the radical.
Isn't the same as x is 2 over 2 to the power of 3?
Now it looks like it though, if I say square root of x squared. Okay, but yeah, I guess you're right. All right, so we're dividing by x here, and we're dividing by the square root of x squared here. So now rewrite it. What do I have up top? And then in the bottom, it becomes one big square root because a little square root divided by a little square root can be rewritten as one big square root. So that's how I snuck that square root of x squared in, and now it's just 2 plus 1 over x squared. So now I can actually evaluate the limit when I take the limit. Okay, so limit as x approaches infinity is what? So 3 over square root 2. So we have a horizontal asymptote at 3 over the square root of 2, which I can rationalize, sure, and make it 3 root 2 over 2. But that's just to the positive infinity direction, okay? Now the issue is, because that's a radical in the denominator, I'm taking the square root. It's like there's a positive root and a negative root, okay? So when I go in the negative direction, I need to take the negative root. So, and that's the best way I can explain this. So I need to do this again. Limit as x approaches negative infinity of the function. So when I do that, I need to think of this now as this root being a positive root and a negative root. So now there's a negative sign in front of that radical. What does that do to my result? Yeah, it just basically changes the sign. It doesn't change the fact that I got a square root of 2 in the denominator, but now it makes it negative. So what's my result? Negative 3 over square root 2, which becomes negative 3 root 2 over 2. So I have two horizontal asymptotes here. One at positive 3 root 2 over 2, one at negative 3 root 2 over 2. And if I graphed this guy, I would see two horizontal asymptotes. Okay? So you got to watch out for these radicals that show up in a denominator of a rational function so that you don't miss one of the horizontal asymptotes. They don't show up very often, but when they do, it's easy to miss one. Okay? So we have two. Okay, limits of trig functions. So find each limit. The limit as x approaches infinity of sine x. What do we know about the graph of sine x?
It curves. It's wavy. It has the.
It's wavy. Curves.
It has the horizontal asymptote. I guess not horizontal asymptote, but like doesn't go beyond a certain point.
What does it do as the graph goes on and on and on? There's a good word that starts with O. It oscillates. The graph just does this. Does it get stuck on a horizontal line? No, it oscillates between two horizontal lines, but that's not what a horizontal asymptote is. Okay? So what is the limit as x approaches infinity of sine x? What is this notation right here asking for? Yeah, what is that asking for?
That the y value where it can't exist.
No, it's asking for...
The horizontal asymptote.
Thank you. It's asking for a horizontal asymptote. Is there one here?
No.
No. So you say does not exist. Okay, now how about the limit as x approaches infinity of sine x over x? And by the way, the answer to all of my questions was sitting right here. Since sine x oscillates between -1 and 1 forever, the limit does not exist.
Well, I mean, I thought if I said
The limit does not exist. Does not exist.
I thought if I just said it doesn't exist, you'd say, but why?
Well, maybe I would. But now I lost interest and I want to move on. So, limit as x approaches infinity sine x over x. What is this notation asking for? It's asking for you to find if there's a horizontal asymptote. So, sine x over x. Now we look down below, since it seems like my answers to my questions are down below. Since -1 is between -1 and 1, kind of bounds sine x, right? Sine x lives between -1 and +1. If I divide -1 is less than or equal to sine x is less than or equal to 1 by x. So I divide all three of these guys by x. Then I have this line sitting right here. -1 over x is less than or equal to sine x over x is less than or equal to 1 over x. Then if we take the limit of each of these three parts, the limit as x approaches infinity of -1 over x is 0. We know that from earlier. On the left side, the limit as x approaches infinity of 1 over x is 0. Again, we know that from earlier. So now we have 0 here is less than or equal to, this should be over x, sorry about that. The limit as x approaches infinity of sine x over x is less than or equal to 0 on the right-hand side. So 0 is less than or equal to something is less than or equal to 0. What must the limit as x approaches infinity of sine x over x be if it is stuck between 0 and 0? It must be 0. Okay? So therefore, we can conclude that the limit is 0. It has no choice. It must be 0. This logic that we just did here and a little bit of math is a demonstration of something called the squeeze theorem. The function that we were looking at got squoze. Yeah, you like that one? Got squoze between two other functions that we knew and could evaluate, and therefore, because it was permanently stuck between the other two, we were able to evaluate the one that we didn't know, and that's the squeeze theorem. Here is the squeeze theorem officially. If h of x is less than or equal to f of x is less than or equal to g of x. So what it's saying is f of x is always between h of x and g of x. So this function is always between two other functions in an open interval containing some number c, and the limit as x approaches this number c of h of x is equal to L, same as g of x. So the two outer functions have the same limit. Then that means that the inside function, the one that's between this guy, the one that's between the two outer functions, must also have the same limit. Okay? So in that last problem that we were just looking at, here is the graph of 1 over x right here. Here's the graph of -1 over x. And then here is the graph of sine x over x right here. And you can see what happens. The graph of sine x over x is stuck between those other two graphs. And as x grows larger and larger, sine x over x continues to oscillate, but it is stuck between those other two functions. So in the end, what happens is the oscillation just gets smaller and smaller and smaller. In engineering, we would say that it's being dampened. And eventually, it dampens down to 0. This is like a vibration, okay? Something that's vibrating or bouncing, kind of like bounces back and forth. Eventually, it stops vibrating or bouncing, okay? And this is kind of what's happening here. All right, so applying things to real life. Suppose this function represents the oxygen level of a pond, where f of t equals 1 represents the normal unpolluted level of oxygen. When t equals 0 weeks, quote unquote, organic waste, I'll let you imagine what that might be, is dumped into the pond, and as the waste oxidizes, the oxygen level recovers using the function above. What percent of the oxygen level exists in the pond after 1 week, 2 weeks, 10 weeks, and then finally, does the oxygen level ever fully recover? What should we do?
Well, shouldn't we find all of the values of t first, I suppose?
I suppose. So,
T equals to f of 1.
okay. So f of 1 week after the organic waste, so whatever this pollutant was that was dumped into the pond, 1 week in, what do we get?
1 over 2.
1 minus 1 plus 1 over 1 plus 1, which is 1 over 2. Okay, so as a percent, that would be 0.5, so 50%. So 50% of the oxygen level that was in the pond to begin with is remaining, okay, or back. So f of 2 weeks now. 2 weeks after the waste was dumped into the pond. What do I have? Plus 1 over 4 plus 1. So that is what? 3/5. As a decimal, that would be 0.6, so 60%. So we recovered 10% in a week. And then next would be 10, so f of 10. Okay, 100 minus plus 1 over, okay,
It's 91 over
91 over 101. Oops.
Using 91%.
Yeah, well, give me the real number.
How much do it?
So we can call it to 3 decimal places 0.901.
Yeah.
So 90.1%. Okay, after 10 weeks. And then finally, does the oxygen level ever fully recover? What is this asking you to find? Okay. Limit as t approaches infinity of f of t. What do you get? No, you don't.
Yes.
No, it's not. Why 1 over 1? The degree of the numerator matches the degree of the denominator, so therefore it's the leading coefficients of the degree of the numerator and denominator, which is what? 1 over 1, which is 1, which would be 100%. So answer the question. Will the oxygen level ever fully recover? No, why not?
Because T has to be infinity to be
Because time would have to be infinite before the oxygen level fully recovered. That's correct. So what does that tell you about pollution?
it's a good thing.
It's a good thing?
It's a good thing, and we should make polar bears eat our garbage.
Time infinite if we want to solve all.
If you have more plastic waste and microbes and fatty acids,
What does that really tell you about pollution?
it doesn't go away.
Yeah, basically, correct. So, and this is real. So it's actually kind of an important problem.
So start dumping bodies into rivers.
Right.
Seagulls eat plastic.
Why don't you dump your bread in the river if you die? Let's try to reach.
The slant asymptote, we talked briefly about it earlier, and let's see if we can get it done here. In addition to vertical and horizontal asymptotes, there's also a slant asymptote. So in these situations, the function goes infinite as x approaches infinity. Use long division to rewrite the function. The slant asymptote is the resulting linear part of the answer. So in this example, notice that the degree of the numerator is 2 and the degree of the denominator is 1. The degree of the numerator is exactly 1 higher than the degree of the denominator, and that is the giveaway that we have a slant asymptote. There's clearly no horizontal asymptote because the degree is higher than the degree of the denominator, okay? But there is a slant. So what we do is we perform long division, or if it's easy to do, you could do synthetic division here, but I want to refresh your memory on long division. X plus 1 divided into the numerator, 2x squared minus 4x, and then any missing terms have to be included, so minus 0. Or plus 0 for the plus. And then what you do is ask yourself, x times what is 2x squared? And the answer is 2x. So you write that above the same degree term. And then you distribute. 2x times x is 2x squared. 2x times 1 is 2x, so plus 2x. Change the terms, signs, so that you can add. 2x minus 2x squared is gone. And then you add here, and you have negative 6x. Bring that term down, plus 0. And then do it again. X times what is negative 6x? So negative 6. Distribute, negative 6x, and then negative 6 plus 1, or times positive 1 is negative 6. Change all your signs and add, and you have 6. That 6 is a remainder, so you write plus 6 over x plus 1. So this 2x minus 6 plus 6 over x plus 1 is the function. You've just carried out the division as far as you can go. This 2x minus 6 right here, 2x, that's an x. This part right here is the linear part of the function. The resulting linear part of the function is the slant asymptote. That's your slant asymptote right there in the graph. That equation would be your slant asymptote. 2x minus 6, y equals 2x minus 6 is the equation for the slant asymptote. So that's how you find it, okay? When the degree of the numerator is exactly 1 higher than the degree of the denominator, there's a slant asymptote. And the way that you find the equation for the slant asymptote is you perform longer synthetic division than the linear part of the answer is the equation for the slant asymptote.
So the top term was 2 degrees higher and no asymptote.
There would be no asymptote at all if it was anything more than 1 degree higher.
Why do we not count the 6 over x plus 1?
It's not that we're not counting it. It's just that this linear part right here is the equation for the slant asymptote. Okay? This part right here would be in charge when x is small. So this stuff, this interesting stuff that's happening here and here is what would be in charge when x is small. But when x becomes large, then the slant asymptote takes over. Okay? So that's it for this section.